Hello. So today we will be having discussion on with weekends content, and likewise we did in the previous cases. Similarly, we will be addressing the challenges of the system, how the system, how the microgrid operation works, etc. So before that, let me wait for a few minutes and make the system fit. Let's wait for 2 3 minutes, and we'll start. So today we would be focusing on various aspects like the simulation, how the simulation or case studies of AC smart grid, AC microgrid are done, AC-DC hybrid microgrid, and DC microgrid. First, we will go step by step. First, we will do AC microgrid, then DC microgrid, then AC-DC hybrid microgrid. Okay, and then some demonstration things. So demonstration, it would be better if we work on physical hardware setup, but won't be much possible. So we'll switch on to question and answers. So let's start today's discussion. So first of all, what is the need of this content? Okay, let me switch from the recording on that. Okay. So first of all, what's the need of continuous real-time simulation? So as we all know that whenever we were trying to replicate any system, okay, so during those cases, since power systems or distribution systems are working physically, which would anticipate some challenges to the users, because if we directly go on testing field and try to implement any such cases on field on the ground, So what we try to do is we just uh, try to replicate those same systems in the practical softwares that we have, and these softwares are quite effective in modeling. Means if we can model them correctly, then the response that will be obtained from these softwares are quite similar to the ones that we will get from the field. Yes, there would be some practical challenges, but yet we are on better side to know at least to go at least near to what people will practically face in the directly on the field. And here, from these outcomes, we will get an overview and to make some changes or to make some modifications that also we can do effectively in the software. So that's one thing. And so here the microgrid, as we all know, that switching into the microgrid architecture, microgrid domain, that is because uh, nowadays the hardware systems that we are designing that are mostly upgrading day by day, and the necessity, the advancements that we are getting using these hardware setups are far more effective and practically the loads are highly changing. So uh, if the consumers will be made much more sustainable by themselves, that would effectively cause some advantages to the grid utility people. So that's the major aim why we are trying to implement these microgrids and test their operating phenomena. Okay. So microgrid analytical studies can be performed much faster with offline simulation programs. Here, what we get to know is that detailed modeling. So what we discussed is that detailed modeling, if we perform, that leads to identification of some challenges that we will face in the physical system. Okay, by physical implementation. So we have various softwares like SCAD, and we try to replicate these things into them. So continuous real-time simulation involves microgrid analytical studies and can be performed much faster than the offline simulation programs. And since the simulator operates the continuous real-time, the simulator system will operate in a manner similar to the real microgrid system, as we have already discussed. So as the simulation parameters are modified and the contingencies are applied, the user can watch the microgrid system's response in real time. So you can get to know the system behavior in real time. Hardware loop testing, the HIL capability of real-time simulators allow the design of operation of the microwave control protection. So operation microwave control protection power devices to be evaluated under realistic operating conditions before they are installed in actual approved system. So hardware loop testing, HIL testing. So there are other modes of operation too, where we all know that controller hardware. Okay, phones, PHIO. That this one which is discussed here, that is known as PHIO, power hardware. And this is known as controller hardware in loop. So once we have, first we like to test software in loop. SIL. And one by one we will get to first SIL. Then if controller and all these things are needs to be tested, then we go for CHIL. And once CHIL is done, then we directly go for power hardware in loop, or we call this PHIL, or simply HIL. So, what the advantage that it provides is that it mimics the entire system, and as a result, we get to know the responses of how the system behaviors, how the current voltages would be affected. Using this, we can also go for planning studies because microgrid ultimately it's a distribution system. So we have the distribution system planning studies that we all know. So here in this case, we need to go for microgrid setup, means how the optimal locations of the DGs can be placed. Okay, so here we can see AC microgrid test case. So AC microgrid, we all know that we will be having a grid side. This is the grid side, and this is the point of common coupling PCC. And from the other side, on the other side, we have the AC bus. This is the AC bus. Okay. So here we have a lithium ion battery and the diesel generator, AC load, PV. So in all these cases, we have to feed power to meet the load demands. Here we have an AC load demand of 0.5 megawatt. So each and every equipment should participate to fulfill that load demand. Okay. So as we all know that the need for battery in microgrids is already been discussed. That in using these batteries, the advantage is that since we don't have the inertial support, that sudden dip or rise in power, so to tackle those things, so it can really deliver that much amount of real power to the grid, so that the system advantages can be minimized. Okay. So we have a battery is generating in DC, it's giving power, so it has to be converted to AC before feeding to the breaker. And whenever we are in excess of power, so sometimes what we need to do is that we need to, uh, as we all know, we are familiar with the duck curve. Okay, so as the day by day we are moving on with the renewables, renewable integration with the clear manner, because as we are going or trying to implement more and more renewables. So what we have is that on morning peak or evening peak. Okay, but now here we have the solar. Okay, so solar is delivering the most amount of power from the as far as the renewable energy is concerned. Okay, so what it can do is that from this point onwards, it starts uh, as we are moving on with the solar units. So it's doing advantageous thing is that it is delivering more and more solar power. But the problem is that the loads are more peak loads occur in these two instances. One is the morning peak, another is the evening peak. So the problem is that during this period of time, the duck curve is getting lower and lower. So because there now it is getting lower because the solar is installation is getting more and more. So the advantage, but the load is not also not present. So what we need to do is that we need to shut down more and more equipments to tackle these circumstances. Okay, so what is generally done is that during these hours, now one thing can be done that to uh, make the PVs working off MPPT. So one option is that we can make the PVs working off MPPT mode, but that is also a challenge because when it is delivering its maximum, then why to misuse that amount of power, that we are energy that we are getting from the solar. So what we try to do is that we try to integrate uh, batteries into the system. Okay, so these batteries uh, are like the pump storage plants. So previously also we have discussed the pump storage plants. So here's upper dam, here's a lower dam, and there's a pin stop. So water which is stored here is opened, the turbine rotates, and accordingly the power is generated. And the major aim of using these pump storage plants are during the to meet the peak demands, meet peak demands. And why to meet the peak demands? Because we need to maintain the frequency, maintain the frequency. Okay, so that's the major aim. We need to have a check on the frequency regulation. So frequency needs to be within that prescribed range. Otherwise, the system would desynchronize. Equipments or synchronous generators would start desynchronizing. So the problem with this is that it, it costs and it consumes major areas. Although it's a good good amount of power that can be generated, and during the off-peak hours, likewise during this period of time. So what can be done is that water can be during the peak hours it is moving this stored, and during these off-peak hours it is moving this one. So using these amount of excess energy, because all are working in MPPT. So what can be done is that it it gets stored, it gets stored in the it gets stored in the upper dam. The water again gets stored in the upper dam during using this excess amount of energy, rather than, because day by day the curve goes on, this sudden changes, these changes and these sudden rise and sudden fall. These two needs to be mitigated using more accurate and we can say more accurate control actions needs to be ascertained. Whereas if you can make the curve stay in this line, then the rise or fall comparative to the rate of change is lower. So when the rate of change of the power that is required, or the load that is required, is lower, then the advantage is that the control actions can be within the prescribed limit, because the experience of the control operators with the operators or the control engineers would become tougher. Life would have been tougher, because what we have seen that during the COVID days, that in India for 9 minutes we had to uh, switch on. We switched on the lights and fans and everything, and the entire current country's load dipped around 75 megawatt, which I can recall. You can definitely go through the paper of Power Grid or Grid Control of India, Controller of India Limited (GCIL). There you can see that how tough it has become to regulate the frequency or to maintain the frequency within the prescribed limit during those times. So that gave to the uh, rise of the batteries. So to replicate the working principle of these pump storage plants, which majorly aims to deliver the electricity during the peak hours, there came the importance of the batteries. So what can be done in the microgrids is that during off peak hours, or during any off peak hours, when rather than working in off MPPT, the because working in off MPPT means we are losing the amount of energy that we have or that is being generated. So why should we do that? So we can directly charge the batteries, and accordingly we can store them in the batteries, and when needed we can use the uh, energy stored in the batteries to meet the certain deviations, or to deliver power during the off-peak time, because in those cases the electricity that is generated could have been here, and this amount of peak part could be can be delivered by the batteries. So the uniformity of the control strategies would stay in a good shape. So that's the importance of using batteries. And the diesel generator, another one thing what we have seen in this diagram is the diesel generator. So with diesel generator, uh, the advantage of using diesel generator is that once we are off grid, means once we are uh, working in grid forming mode. So in those cases, what we need to do is that the generators delivers the power, excess power, like the slack bus, okay, and it also takes care of the reference angle of the system, okay, because you have to have a reference angle to perform the load flow solutions, and using those load flow solutions we can get to know the voltage magnitude and the angle, and using these we can restructure again to obtain the entire power flows in the entire system, okay, restructure the power system operation. Or we can rather say microgrid operation, since we are discussing about the microgrid here. Okay, so accordingly we can set our control operations and other real-time situations like to perform. Well, nowadays the DSO model, DSO concept is also getting uh, enriched day by day with the white paper being submitted to the government by IIT Kanpur, IIT Delhi, and PERI, the Engineering Research Institute. So now government is looking up all these features to find out whether the model of DSO, the need of DSO in the electricity markets to control the DSO in the electricity markets, because there we need to have the aggregators with the large number of EVs coming into the picture, buses, the smart cities, and all these things. So the model of DSO is getting more and more prominent nowadays. So similar is the case, the DSO model needs to be formulated for the microgrid system also. And in the microgrid system, what we see is that uh, the we can also consider them as microgrid operators. Okay, because distribution system, yes, they are a part of distribution system, but they are working centrally. Because once it is off grid, okay, from the point of common coupling, if the grid is out, then we can definitely say that the system is off grid, and we can get to have the outcome as follows. So here it's a test system uh, from the DC-AC converters, since solar is generating in DC. So DC-AC converters, and generator is generating in DC itself, sorry, AC itself. So it is not requiring any AC-DC controller system. So there are some case studies which have been performed in the RTDS. That here, first of all, systems with this red means that the system is inoperative. It is also same. This also same. So in such cases, with this model as discussed previously, as shown previously, this is the similar model which is developed in RTDS. And what we have is that we have a grid bus which is feeding the load of zero point 0.5 megawatt. Okay, rest are all off. They are not delivering any power to the grid. Okay. So, so here the grid is directly feeding 500.501 megawatt. Okay. And the load is consuming 0.5 megawatt. So the rest are acting as the losses. And in those cases, these currents are at zero battery current, PV current, generator currents, but grid currents are at its maximum values 0.85427 kiloamperes. Okay. So point of common coupling currents are also using a value. Whereas in the grid connected mode, case 2, where we suddenly perform a load switching, okay. So here we can abruptly see change in the system. Okay. So again, this is for the same the point of coupling currents. Again, for grid case 3, we have the speed connected mode of operation where all are switched on, and we are having accordingly the powers for the system, the current flowing into the system. So one by one, if we go here, DER, absent, grid is feeding the power. Okay. In this case, DER is still disconnected. Okay. Now the battery is switched on. So this is charging. Increase of MPPT. Diesel unit is diesel unit is delivering the voltage regulation. Okay, so that's the challenges that we are facing right now. So these are some of the operating cases. So okay, just give me 3 minutes. I just come within 3 minutes, 3 4 minutes. So I was feeling unwell. That's why just took 5 minutes for time. So this is the diesel unit, and then we have DR switch lamp, and voltage support. Okay. And lastly, we have charging, we have MPPT, frequency support. And this is the case for switching. The transients can be observed. Transients can be observed, and this is the steady state. Acha, voice not audible. Now is it audible? Steady state operation that we have discussed right now. Okay, thank you. So there are circumstances where we face the same problems with some problems with related to which related to the PV and wind. So there, what we can get to know is that, let's suppose we have a grid here. Let's suppose we have a grid here, and from this grid we are supplying PV at this point, and it is operating in MPPT. Then we have battery energy storage systems BESS, which is delivering a two-way power. Means it is during the peak hours it is delivering power, and during the off peak hours it's absorbing the power to maintain the frequency of the microgrid. Then we have wind, which is also working at MPPT. But the problem is that during the day this works, during the night mostly it is seen. Not always true, but yes, mostly it is seen to work in night. So that is the point of time where, and here we have loads that we need to deliver. So there are instances where the generation is more than the uh, generation is generation is more than the absorption, the load power that is required, load demand. So in those cases which is generally observed for PV in the daytime and wind in the night time. The best way is to store that amount of energy to be used later on. Okay, but still it has SOC limitation. We also need to take care of the SOC limitation. The SOC limitation should not violate because it is 20% on the lower side and 80% on the higher side. Although above 90% when it reaches electrical charging on these phenomena are generally comes into picture. Okay, so actually I'm not feeling well. That's a problem. Okay. So here's a DC system. Okay, now that was mostly AC. So in the DC system or DC AC, DC microgrid, standalone DC microgrid, here we can see PV panels, DC generators, batteries, supercapacitors. So this is the DC bus. Okay, and it is feeding to the grid using a DC-DC converter to uh, control the operating scenario or control the terminal voltage to meet the load power, because ultimately we need to maintain the voltage to a specified limit for the bus because loads are directly connected. Okay, so here we can see a wind. The wind is generating in AC. AC to DC conversion is taking place in the first step, and then we have DC-DC converter to provide a control DC in the output side. Okay, so here we have loads. Some loads we have. So these are some buck boost converters as you can see. Now in this problem we should always think of the optimal DG placement, because optimal DG placement needs to be formulated or framed right away. Okay, so here we have DC microgrid, then we have a DC microgrid 2, microgrid 1, microgrid 1, microgrid 2. So here we have a bidirectional converter. So if it is needed to share the load amongst these converters, then what we try to do is that we stage the load bus accordingly, and from these things, this is we can also say uh, networked microgrid. Okay, these two microgrids are networked with each other. The advantage that it provides is that the system becomes cost effective. The system also becomes reliable. Quality of power of can be maintained. Quality of power can be maintained, and some security benefits. Whenever the one side of the microgrid is supposed to have uh, low load sharing. So likewise in the transmission system that we all know that there are cases where area 1 feeds to the area 2. Similar is the case here. Okay. So So this is the architecture that we can see interconnection of two microgrids. We can also see the system to be a networked microgrid in place. Okay. Control action is automatic if we can uh, develop a DSO model and implement them for microgrid. So if area 1, area 2, so area 1 greater than area 2 and the load demand. The load demand area 1 is greater than area 2. But for generation, let's say 2 is greater than area 1. So area 2 can definitely deliver power to area 1. Okay. So here we need to keep in track of the interactive current. Okay. This is the common current which is flowing between these two systems. Okay. So we need to keep track of the filter properties that advantageous filter properties should be kept to maintain the system level so that parallel operation can be assured. So challenges in parallel operation. Here we can see inverter 1 in parallel with inverter 2. Now we have, let's say, generation capacity that needs to be delivered. So parallel inverters current sources. Okay. So here we keep LCL filter. The closed loop gain becomes G1 is equal to V01 into I21 21 I21 divided by E into V01. Now we have two parallel inverters. Okay. So I21, I22, G11, relay transfer matrix. In this way, we can find out the current flowing through the inverters. Okay. For the interactive mode of operation, so we can get to find interactive current as beta F2. Okay. So two part are there, common current and interactive current. So common current you can find as IF2. So for stable operation, we all know that poles should be on the left side. According to the zone of potential stable, unstable, if it is on this line, that is all know, we all know marginally stable. Okay. So we need to just check that between this interactive and common current, the poles should never go to the right hand side, should always be on the left hand side. Okay. Okay, yes, let me switch on fan because I'm feeling hungry. I'm feeling hungry. Okay. So I think it's visible. I'm feeling very hungry. Yes. So here we have the power quality mitigation techniques where we all know that we generally use FACS devices. Okay. So what are FACS devices? Flexible AC transmission system. So similar to the FACS devices, defects, the distribution facts. Okay. So we generally use some compensation techniques. Okay. And to improve both voltage and current improvement to ultimately improve power. Okay. So these are some harmonic mitigation techniques. You can see this is the experimental CHIM control hardware in loop setup that was tested and how the harmonics have been filtered to obtain the smooth, easy waveform without compensation and with compensation. So you can clearly observe that the voltage waveforms are more towards sinusoid in this using this compensation. Okay. So this compensation block, this is the controller. So major cause of using is that it occurs uneven switching. Next, it may lead to nonlinear operation. We may also have ACDC drives operation. So the major problem, these are the cause. Switching nonlinear operation, ACDC drive operation. So the major problem lies in they lead to harmonic currents, leading to overloading or overworking scenarios. So that was the overview. Okay. So of this understanding. So we can take 2 minutes break because just to have I'm feeling very unwell. So we'll start with the question. Just 2 minutes break. Okay. And in the meantime, if you have any questions, you can put up. Okay, let's start. So we'll have some question answer discussion. Please give some time to write the questions. I'll put up one by one. Okay. So please answer. Park's transformation is used to transfer from alpha beta naught to ABC, DQ naught to ABC, ABC to alpha beta naught, ABC to DQ naught. So any answer? Any guesses? Any guesses? Then write in the chat box. A. No, A is not the correct answer. A is not the correct answer. is one. So we have started discussing the question and answer. So Parkes transformation is used to transfer from alpha beta 0, alpha beta naught to ABC, DQ naught to ABC, ABC to alpha beta naught, ABC to DQ naught. Yes, D is the correct answer. D is the correct answer. It differs from ABC to DQ naught. So then we have next question. Energy management strategies in DC microgrid aim to A. Increase the stress energy storage system. So the question is energy management strategies in DC microgrid aim to number one increase the stress on energy storage system. Number two reduce peak energy deficit. Number three degrade the lifespan of the energy storage. Number four extract maximum power from PV and wind. B. Reduce peak energy deficit. Okay. Yes, this is the correct answer. Yes, this is the right answer. For the next question. Just wait a minute. মাথা মাথা ঘুরছে বেশি হাত দিয়ে তুলে যাবে পরে। Yes, I'm writing down the possible options. Steady state stability. Or so which stability involves a response to small disturbances that occurs in the microgrids producing oscillation. Steady state stability, transient stability, dynamic stability, and all. See, okay. Yes. Dynamic stability. Okay, next question. Wait. 对，我 4. Which one? So, group control. So which one is the type of advanced loop control technique? Loop control, power line signaling, voltage leveling, virtual resistance based loop control. Option D. Yes, D is the correct answer. Find my correct statement. Statement 1. These are not options, these are statements. Yes. Ah, so with its energy management system, this is the first statement. The second statement is so these two are statements. So based on these two, option only one is correct, only two, both, none. So find the correct statement. So first of all, a hybrid storage system combines a battery with its energy management system and ultra capacitor. Okay, this one is the first question. And the second question is the ultra capacitor is a low energy and high power density device. So out of these, you need to select uh, the options. No, one A is not correct. So D is also not correct. D is also not correct. Hybrid storage system combines a battery with its energy management system and ultra capacitor. Okay. The next question is next segment is the ultra capacitor, the low energy and high power density device. Yes, but but ultra capacitor, okay, but ultra capacitor is a high energy capacitor. Yes, high energy capacitor, but it also has the possible ability to deliver high. Uh, yes, it can be said mostly it is considered to deliver high power, but and sometimes based on scale, it can be considered to deliver both high power and high density energy density. Okay, so in this case, although it was written yes, the problem, the statement that you have raised is correct, but here the solution it is given. So for the time being, let's stick to because it should be high. So only one. Yes. Okay. Which of the microgrid has a DC bus? As its main bus. This is a comparatively easy question. AC, DC, hybrid. One. Which one of the microgrid has a DC bus? This is a comparatively easy question. which is correct. Hybrid microgrids. Okay. So some options are communication infrastructure development, okay, then power management, economic challenges, economic concern, all. Only communication. Hybrid microgrids, only communication framework, nothing more. Yes, all. Eight. What are the control variables in a microgrid? P and Q, V and F, PV and F, PV, F and Q. Any answer? Any answer? PVF. No, it's not correct. It's not correct. Not PVNF. No, this is also incorrect. Any answer? What are the control variables in a microgrid? P and Q, V and F, PV and F, PV, F and Q. Yes, D is the correct answer. D is the right answer. Which of the following is an intelligent control technique? Virtual impedance method, angle group control, multi-agent controllers, all of the above. None. No, none is wrong. None is wrong. Which of the following is an intelligent control technique? Virtual impedance method, angle group control, multi-agent controllers, all. Any answer? Multi-agent controllers. The major drawbacks. What is the major drawback of voltage level signaling? What is the major drawback? of voltage level signaling. It is a nonlinear form of voltage drop. Number of sources in the system is restricted. Significant voltage deviations are permitted. None of the above. C means significant voltage drop deviations are permitted. No, it is wrong. C is wrong. A. It is also not correct. It is a nonlinear form of voltage drop is not correct. A is also incorrect. No, G is also not correct. So C, A, D, all three are incorrect. That means we are left out with one option, which is the correct one. The number of sources in the system is restricted. But the number of sources that we can attach, it is mostly restricted. So to have voltage level signaling, that's the major challenge. Due to voltage drops over long distances, yes. Dash. So high potential difference based control. This is a type of decentralized microgrid control. So high potential difference based control, self discharge based control, DC bus signaling based control, and none of the above. DC was signaling response. Yes, correct. A two-level inverter. In two-level inverter systems with similar inverters, the interactive current for both the inverters will be equal in magnitude but out of phase, unequal in magnitude but out of phase, neither equal in magnitude nor out of phase, all. Any probable answer? In two-level Inverter system with similar inverters, the interactive current for both the inverters will be equal in magnitude, not out of phase, unequal in magnitude, not out of phase, neither equal in magnitude, not out of phase, all. B. Yes. Unequal in magnitude or out of phase. So, a diesel generator is capable of injecting active power in the cost of reactive power absorption, as well absorbing reactive power only, injecting active and reactive power both. Any answer? It will inject both active and reactive power. Okay. Our last question that will take off for today. similar inverters. No. In two-level inverter system with similar inverters, if the current references on the current control loop are equal, then only interactive current exists, only common current exists, some harmonics will also exist, none of the above. Yes, correct answer. So with this, we are done for this today's discussion, and okay, we have had some question answer discussions. So I'll upload these things and upload the recorded videos. You will get access all these things accordingly. And any questions if you have, you can put up, or we'll meet on the next Saturday. Next Thursday we'll meet because next Saturday the class the time schedule will be shifted. So you'll get the mail officially from the NPTEL site, and the class will be on Thursday 4 to 6 p.m. Thank you very much. Thank you for your kind attention. Thank you.